Hey guys, so this here was the last question of our Integration Extension 1 exam, and it says suppose that there exists a differentiable function f and we've been given an equation below. And the first part is show that f of 0 is equal to a half. Now, it's pretty difficult to evaluate what this integral is because we don't know what f of x is, and since there is a t in front of f dash t, we can't just use our reverse chain rule or our fundamental theorem of calculus. So what we need to do is let x equal to 0 and sub that in. We'll get 3 of the integral between 0 to 0 of t f dash t dt, and then we'll also get 2 0 plus 1 f of 0 minus 1. So what I want to point out is that the integral of anything between one bound to the same bound, or 0 to 0 even, is always just going to be 0. And what we'll have is 2 f of 0 minus 1. Now hopefully we can recognize that we want to make f of 0 the subject, so in doing that we'll get f of 0 is equal to half. So for our second part, it says hence or otherwise find f of x. Now what many students struggled with is a tunnel vision into trying to evaluate this integral. Now there is actually another way we can get rid of an integral sign, and it's through the opposite of integration, which is differentiation. So if we were to differentiate both sides after a little bit of manipulation, we should be able to create a new expression for this equation. So first, what I want to do is let's suppose that there's a capital F of t, and this capital F of t, or f of x, is going to be the primitive of t f dash t. What that means is when I differentiate f dash t, or capital F of t, I'm going to get t f dash t. Now let's evaluate this integral, but using our new defined primitive of f of t, or capital F of t. We're going to have our bounds of 0 and x, and it's going to be 2x plus 1 f of x minus 1. Now subbing in those bounds, we're going to get 3 f of x minus f of 0 is equal to 2x plus 1 f of x minus 1. Now, so what we can do is differentiate both sides with respect to x. So that will be 3 capital F dash x is equal to, and I'm going to use the product rule on my right hand side. So that's going to be 2 f dash x of x plus 1 plus, and then 2 f of x, and the derivative of x plus 1 is just 1. Now capital F dash x we just defined as t f of t, f dash of t. So we can replace that with 3x f dash x, and then we're going to expand, so that's 2 f dash x plus 2 f dash x plus 2 f of x. Now what I'm going to do is move all my f dash x's onto my left hand side and keep all of my f of x's onto my right hand side. So we get f dash x minus 2 f dash x is equal to 2 f of x, and we can then factorize, so we get f dash x minus 2 is equal to 2 f of x. Now this might be hard to spot, but this is actually a differential equation, and it's easier to see when I let y equal f of x. That means that dy dx equals to f dash x. So if I sub that back in now, we know that dy dx times x minus 2 is equal to 2y. So let's solve this as a differential equation. So we get dy on 2y is equal to dx on x minus 2. And we integrate this, and we have our initial values of when x was 0, we had a half, right, from part 1. And we had x and y as our upper bounds. So we'll get a half ln y between a half and y. And then we'll also get ln x minus 2 between 0 and x. So then we can evaluate this to become a half ln 2y when we put in our bounds, and we'll get ln absolute value x minus 2 over minus 2. Now I want to make it very clear that since we're going from 0 to x, we still need our absolute values. But since we're going from half to y, we don't need our absolute values on our right hand side. Now, exponentiating both sides, we'll get the square root of 2y is equal to the absolute value of x minus 2 over, and then we're just going to leave it as positive. We've used our absolute value. So squaring both sides, we'll get 2y is equal to x minus 2 squared, and notice we don't need our absolute values because I've squared it now, over 4. So y would be x minus 2 squared over 8. And so that is our final solution for f of x if we just replace y with f of x. We get x minus 2 squared over 8. So if you want to see more integration questions like this or any other difficult questions, feel free to tag along to our exam program coming up.